Alright, today we are on page 124. I just want to do one more graphing problem on rational functions before we move on to radical functions. So we graphed a couple already, just following the steps that we took on pages 119 and 120. We're going to do the same thing today. It's just in this example, something happens that we have not seen yet. So I wanted to make sure to include it in the notes. Alright, so this example, it's already factored for you, so that's good. If it wasn't, I like to go ahead and factor from the beginning. You don't have to, but you're eventually going to have to factor anyway. So you might as well get it out of the way, but this one's already factored. So if you recall, on page 119, step 1, find the x-intercepts of the function. Substitute a 0 in for y and solve for x. Okay? Lost my spot. So we're going to find the x-intercept. So if you want to know what x is equal to, plug in a 0 for y, and then the only variable you'll have is x, so then you just solve for x. Okay? So I'm going to take my equation, my function, 0 equals x minus 2, all over, or quantity divided by x plus 2 times x minus 2. Now, we could cross multiply here because we have a fraction set equal to a fraction or just a number. You could still cross multiply. I just like to clear my fractions. You're pretty much doing the same thing. So I'm going to multiply both sides of the function by the least common denominator, which is x plus 2 and x minus 2. So on the left side, when we multiply x plus 2 times x minus 2 times 0, we get 0. On the right side, x plus 2 divided by x plus 2 is 1, x minus 2 divided by x minus 2 is 1, and we are left with x minus 2. Notice every time we find the x-intercept and we clear our fractions on these, you're always just left with 0 equals whatever the numerator is. Every time. But I'm still going to go through the process because sometimes we forget or we want to apply that to everything. So I'm still going to go through the process. So then just to solve for x, add 2 to both sides. And my x-intercept is 2. We only have 1. You may not have any x-intercepts. Okay? You may have more than one x-intercept. But in this case, we have one x-intercept. I'm going to go ahead and sketch my x and y axis. And my graph will cross the x-axis at a positive 2. Everybody cool with that? Alright. So now, the second step is to find the y-intercept. And that's where my graph will cross the y-axis. It may not cross the y-axis. It may. So to find the y-intercept, this time we'll plug a 0 in for x, and that way the only variable that you will have is a y, so then you'll just solve for the y. So instead of instead of x minus 2, I'll do 0 minus 2, quantity divided by 0 plus 2 times 0 minus 2. So notice the only variable you see is a y. So my numerator, 0 minus 2 is negative 2. Denominator, 0 plus 2 is positive 2, times 0 minus 2 is negative 2. Simplify that, you get negative 2 divided by negative 4. We know a negative divided by a negative is a positive, so you have a positive 2/4 or positive 1/2 or positive 0.5. And that's where my graph is going to cross the y-axis. Halfway between 0 and 1. Any questions on that? So those are pretty easy, right? All right. Now we have to look to see if, and remember, these steps, you don't have to go in this order. You have to find all of these things, but if you don't find them in the same order, one doesn't affect the other. So if you want to find your intercepts first, find your asymptotes first and then find your intercepts, you can do that. Just as long as you make sure you find everything. Okay, step 3. Find any vertical asymptotes. Graphs can have an unlimited number of vertical asymptotes. To find vertical asymptotes, make sure the numerator and denominator are completely factored, which ours are. Cancel any common factors. Okay, so did we have any factors that could be canceled? No. None? We can cancel x minus 2 and x minus 2, right? Okay, so it says, if no factors can be canceled, all right, so if factors can be canceled, called removable discontinuity, the vertical asymptote is any restriction that can't be canceled, okay? So both of those factors in the denominator, they're not going to both be asymptotes because one can be canceled. Now the one that can be canceled is going to be something, but it's not going to be a vertical asymptote. All right? So let me go back to my page. Sorry about all the flipping. We know that the x minus 2 and the x plus 2 can be canceled. So our vertical asymptote, remember vertical asymptote has the y equals, because it's where it crosses the y-axis. No, said it backwards again. X equals, because it's where it crosses the x-axis. X equals basically what can x not equal for the one that's not canceled? Negative 2. So that's my vertical asymptote. So since that was from a factor that could not be canceled, that's also, in case you're asked, called non-removable discontinuity. We would say this graph has non-removable, because we can't remove the factor. That's how I remember it. Non-removable discontinuity at x equals at negative 2. So if I told you, hey, this graph has non-removable discontinuity at x equals negative 2, you go, oh, that's a vertical asymptote, okay? Of course, that's what that means. I'm going to sketch in my vertical asymptote at x equals negative 2. Now that factor that was canceled, we know that we can't have any x values that equal negative 2 or positive 2, right? But the one that was canceled is not a vertical asymptote. But still, there's no point on our graph that can have an x value of positive 2. But we don't draw in an asymptote there. We just draw wherever you see, wherever x is, in this case, a positive 2, that's going to be a hole, okay? So right here, and actually, our graph is supposed to cross the x-axis there, but we have to draw a hole around that because it can't actually have that x value. So like when we get down to drawing our graph, we're just going to place a circle there and we're going to jump it and then continue it. Because you can't have an x value at positive 2, right? But it's not a vertical asymptote. So this was the part when I said I wanted to do this problem because we haven't seen this yet. We haven't had any that had factors that could cancel to create a hole. So that hole, we call that removable discontinuity because that was a factor that we could remove. And removable discontinuity creates a hole. So we have removable discontinuity at x equals, look at the factor that we canceled and obviously change the sign, x equals positive 2. This will create a hole. Now, it just so happened that it was at the same place that our x-intercept was, but it just happened to be that way. It's not always going to be that way. Coolio? All right. Next on our list, we have to find the horizontal asymptote. Remember, horizontal asymptote has to do with how many degrees that are in your numerator compared to how many degrees are in the denominator. So we'll go back and read the little list, but first let's figure out how many degrees we have. How many degrees are in my numerator? 1 degree, right? X's exponent is a 1. The denominator, am I going to have to put that all in standard form to figure out how many degrees it has? No. How many degrees is it going to have? 2. Because first term, as long as these are both in standard form to get alone, first term times first term is going to give me my first term, which is x squared, which is 2 degrees, right? So we have 1 degree in the numerator, 2 degrees in the denominator. So let's go back and see, unless y'all memorized this yet. On page 120, step 4 was the vertical asymptote. Remember, you can't have more than one vertical asymptote. You don't have to have any. If the degree of the numerator is less than the degree of the denominator, is that true? Numerator is less. Then the graph has a horizontal asymptote at y equals 0. So basically, the x-axis is the horizontal asymptote. All right? Does that make sense? Y'all cool with that? So I'm going to sketch that in. Now we have to figure out where our graph is going to cross, or where our graph is going to be. Okay. All right. I know my graph is separated into 4 sections. I've got this horizontal asymptote and this horizontal asymptote. So I have like this section here, this section here, this section here, and this section here. So only points that I really know are going to be up here. So I know I can sketch in here, and don't touch that. It does not go through the circle. That's an open point. And I'm just going to run it along. Now, for some reason, horizontal asymptotes, and I think I may have mentioned this to y'all before, I'm not sure. A horizontal asymptote, it may actually go a little below it. So that's why, like, it's supposed to cross the x-axis at 2, but there's a hole there. Never vertical. But I just kind of sketch it across there. That's all you need to know. You just need to know sketch. All right? So just in case you ever see it go a little below the horizontal asymptote, that's going to happen sometimes. But those are the only 2 points that we know on this graph, right? Could we have part of our graph that's down here below what we just sketched? No, because it's supposed to be a function, and if we did, that wouldn't pass the vertical line test, right? But we may have part of our graph over here on the, to the left of this asymptote, or to the left and under the other asymptotes. So we need to check and see, or we may not, but we need to check and see if we do. So don't pick a test point anywhere from this vertical asymptote to the right, because we already know that part of the graph. So we could test -3, -4, -5, -6. I just like to stay close to the asymptote. So I'd probably just test point -3. All right? Oh, I forgot. We were supposed to check for oblique asymptotes too. That was step 5. Determine if you have an oblique asymptote. This only occurs in rational functions, which is what we're doing, when the degree of the numerator is 1 greater than the degree of the denominator. Well, was that true? No, so we don't have to worry about a horizontal or a slant asymptote, also called oblique asymptote. But just to check. All right, so again, I'm going to pick a test point of x equals -3. I'm kind of out of space. I'll do that up here out of the way if I can. So in my function, wherever I see a x, I'll just plug in a -3. So -3 minus 2 over -3 plus 2 times -3 minus 2 gives me -5 over -3 plus 2 is -1. Remember, we're multiplying. I put parentheses in that thing. I didn't mean to. We're multiplying by -3 minus 2, which is a -5. So we have -5 divided by +5. Simplify, we get -1. So that ordered pair, when x is -3, y is -1. So we know we can sketch in another graph in that region. And remember, you can find more ordered pairs if you want, if you don't feel comfortable where to sketch what, but it's just going to hug the asymptotes. So just figure out what region that your graph is in, and then just make it hug the asymptotes. Rational functions like hugs too. Who doesn't? See how fun this is? And that's all I want to teach you about rational functions and their graphs. Does anybody have any questions on that? Now again, how to figure out what your horizontal asymptote is, what your vertical asymptote is, you just have to memorize that list. That's all there is to it. Because if you know where to draw those asymptotes, figuring out your graph is going to be way more easier than just plugging in a bunch of values for x and a bunch of values for y and trying to figure out what your graph is. All right, so make sure. The vertical asymptotes are a lot easier than the horizontal ones. So the horizontal ones just take a little bit more to sink in. All right, we all good? Anybody need to see any of this paper scooted around? Did you get everything? All right.